He just mentioned a seismic design using structural dynamics. We had a significant number of specific requests for this topic, so I decided to include it, and we will see how it goes. I will specifically, when it says structural dynamics, we will specifically use the so-called modal response spectrum analysis in the design of structures. We will start with BNBC 2020 requirements. This is now section 2.5.6. 2.5 is the section on earthquake loading, as you know by now. This section says equivalent lateral force is allowed. That procedure is allowed, provided both of the following conditions are satisfied. So you can design a structure using equivalent lateral force procedure if two conditions are satisfied. This is different from ASC 7 requirements that I showed you earlier. So the first condition is the building period in the two main horizontal directions is smaller than 4 times T sub C. T sub C is defined in section such and such, and 2 seconds. So the period in both directions is smaller than both 4 times T sub C and 2 seconds. T sub C is what is T sub S in ASC 7, and that is S sub D1 over S sub DS, as discussed earlier. The value of T sub S is typically around 0.5 second. So 4 times T sub C will also give you 2 seconds, roughly speaking. Anyway, so you understand that we are talking about frames that are 20 stories tall or shorter. Those are the ones that can be designed using equivalent lateral force procedure. Also, second condition, the building does not possess irregularity in elevation as defined in section such and such. So there are plan irregularities, there are vertical irregularities that we discussed in detail. Vertical irregularities must be absent for you to be able to use equivalent lateral force procedure as the basis of design. These are BNBC requirements. These are not ASCE 7 requirements. I would say these are more severe than ASCE 7 requirements, but that's what you have, and this is what you have to comply with. Then further on, 2.5.8 of BNBC 2020 says, under dynamic analysis methods, dynamic analysis method involves applying principles of structural dynamics to compute the response of the structure to applied dynamic or earthquake loads. That is just a description, if you like. So earlier slide said equivalent lateral force procedure can be used only under certain conditions. This section 2581 gives us requirements for dynamic analysis. Dynamic analysis should be performed to obtain the design seismic force and its distribution to different levels along the height of the building, and the various lateral load resisting elements for the following buildings. So dynamic analysis should be used for the following buildings: regular buildings with height greater than 40 meters in zones 2, 3, and 4, and greater than 90 meters in zone 1. Okay, so even when your building is regular, If you go beyond 40 meters of height, zones 2, 3, and 4, or beyond 90 meters of height in zone 1, you shall do dynamic analysis as the basis of design. Irregular buildings with height greater than 12 meters in zones 2, 3, and 4, that is not much. 12 meters is like 40 feet. And greater than 40 meters in zone 1. So if it is irregular buildings, then beyond 12 meters in zone 2 and higher, you have to do dynamic analysis, and about 40 meters in height in zone 1. For irregular buildings smaller than 40 meters in height, so 40 meters on, you have to do dynamic analysis in zone 1. But when your building is shorter than 40 meters in height in zone 1, dynamic analysis, even though not mandatory, is recommended. Okay, so a number of things. First of all, these are again BNBC requirements, different from ASC 7 requirements, which I have discussed with you earlier. The thresholds for regular buildings are based on height. For irregular buildings, they are also based on height. The height thresholds are lower for irregular buildings than for regular buildings. Okay. The recommendation, a code typically does not provide recommendation. A code typically is mandatory language document. Anything that is not mandatory, that is not enforceable, is typically not included in the code. But BNBC has given you that recommendation. Something I do want to mention just for you to know, what we have gone through so far in the last few minutes already tells you that BNBC has a lot more faith in dynamic analysis, modal response spectrum analysis than in equivalent lateral force procedure. Equivalent lateral force procedure is allowed only under pretty significant restrictions. But in ACE 722, which just came out, this is the latest ASC 7, has not been adopted by codes, is not in use, but will be in the next couple of years. In ASC 722, pretty much all restrictions on the equivalent lateral force procedure have been removed. Equivalent lateral force procedure has been found to be as good, if not superior, to dynamic analysis procedures, basically for all buildings. So this is something for you to know. This is something I'm sure in your future, but for now, obviously, you have to go with BNBC 2020, and you have to pretend that dynamic analysis gives you better results than equivalent lateral force procedure. Okay, dynamic analysis can be carried out through the following two methods. So there is modal response spectrum analysis and time history analysis, what is also called response history analysis. The modal response spectrum analysis is when a structure vibrates, let us say under earthquake ground motion. Remember, the foundation starts moving every which way all of a sudden in an earthquake. The remainder of the structure, because of inertia, cannot readily follow the movement of the foundation. It stays behind, and then tries to catch up with the movements of the foundation. That sets the rest of the structure in vibration. So when the structure is vibrating, the deformations that it undergoes can be thought of as juxtaposition of, combination of deformations of a number of so-called modes of vibration. So, let me put it another way. We imagine is not the right word. The concept is that the structure set in vibration is simultaneously undergoing vibrations in a number of different modes, which mean in a number of deformed shapes. So the structure is deforming into a number of deformed shapes simultaneously, and the deformed shape of a structure at any particular instant is the combination of the deformed shapes of these fundamental of these shapes that we talked about. These shapes are the shapes of the different modes of vibration, as we call them. They are like single degree of freedom systems, as we will describe. I don't want to go into terms now. Anyway, and so we analyze the different modes like single degree of freedom systems, and then combine the responses of the various modes to come up with the combination of the structure. I know what I did is not the best, but it will become clearer as I take you through the procedure itself. Time history analysis is where we impart actual recorded earthquake ground motion or artificially generated ground motion at times to the base of our structure. When we say impart ground motion, it is typically in the form of acceleration history. We input pairs of time and acceleration. So at this time, the acceleration is so much. At an increment of time, the acceleration is so much. At another increment of time, the acceleration is so much. And for us to get accurate results, the time increments have to be short. So the acceleration history is imparted to the base of the structure, and then we calculate the deformations of the structure from structural dynamics. In this type of analysis, if we assume that the structure remains elastic as it undergoes the earthquake ground motion, then we have elastic time history analysis, which, if you ask me, does not give us any more information than modal response spectrum analysis. So elastic time history analysis is something I personally have never been big on. However, if you recognize reality and assume that in the process of responding to the ground motion that we have imparted to the base of our structure, selected portions of selected structural members become inelastic and undergo inelastic deformations, then what we are doing is inelastic response history analysis, which is the most sophisticated analysis we can do. And for most important projects today, That is the analysis that forms the basis of design. Okay. Entire chapter 16 of ASCE 7 is devoted to nonlinear time history analysis. That is not our topic today. We will concentrate on modal response spectrum analysis, and when dynamic analysis is required, vast majority of engineers would still do modal response spectrum analysis. And that's definitely true outside of the US. In the US, I think things are changing rather rapidly in favor of response history analysis. In section 2.5.9, BNBC tells you about a number of things related to modal response spectrum analysis. First, modeling, then number of modes that you have to consider. Then modal story shears and moments is the subsection title within parenthesis response spectrum analysis. Then structure response, then structure response, modal combination and scaling. Now, what I want to tell you, the main important thing is everything on this page is pretty much the same as what ASCE 7 tells us, except that the modal story shears and moment section, subsection 2593, does not have a lot of content. Just based on that, to do a modal response spectrum analysis is probably not that easy. So that's where I want to provide elaboration. How do you do modal response spectrum analysis? Okay, how do you find these modal story shears and moments? So that is pretty cryptic in BNBC 2020. I will go into as much length as is needed for complete understanding. So we will start with the very basic concept of the response spectrum. This has come up, the term has come up, and we have looked at spectra, but let's fully understand what a response spectrum is, and from that we will go to what we call design spectrum. Now, the response spectrum is directly related to the design ground motion at a site. Design ground motion not at the source of the earthquake or somewhere else, but at the site on which we are going to build our structure, the structure that we are designing. I think I mentioned previously that earthquake ground motion is recorded by strong motion accelerographs. That is what the instruments are called, graph, G-R-A-P-H. The instrument is strong motion acceleroph, and the records that the acceleroph makes are strong motion accelerograms. Okay. The instruments are called strong motion accelerographs because they are triggered only when ground accelerations go beyond a certain threshold, so that every little bitty earthquake is not recorded. Okay, those are strong motion earthquakes generating strong enough ground motion that are recorded. The instruments always record ground accelerations in two mutually perpendicular horizontal directions and in the vertical direction. Okay? So we get three accelerograms. The picture on the screen, which I have shown you earlier, is one of the earliest strong motion records. This is the record of the 1940 El Centro earthquake, as recorded 1940 Imperial Valley earthquake, as recorded at the El Centro, California station. The top is the acceleration, the accelerogram of the north-south component of the ground motion. Okay, so there was a northeast component measured and an east-west component measured, the history of which would look different, and a vertical component also measured. What we are showing you is the north-south component. I have remarked previously that only thing you can say about this kind of ground motion is that it is erratic. And the other thing is that the frequency is very high, the period is low. The period would be from one zero crossing to one extreme to the other extreme to the next zero crossing. That period is very short in the acceleration history. Agencies that record these accelerograms pretty much routinely integrate the accelerograms with respect to time, obtaining a history of ground velocities. And you see right away that the ground velocity plot is not as erratic looking as the accelerogram, and also more importantly, the period has lengthened. Now the time between two zero crossings is longer than in the acceleration plot. The agencies would also integrate this history of velocities with respect to time, obtaining a trace of ground displacements. This ground displacement plot is downright ponderous. It's the period is long. If you compare this with that, it's a huge contrast. Now what you see is for one component of one earthquake, but the major observations hold for any earthquake ground motion. The fact that the frequency is very high in the ground accelerations, it decreases when it comes to velocity, and it becomes, the frequency is very low, the period is quite long when it comes to ground displacements. Okay. I think that may be enough for now. Now, in this figure, we are considering three single degree of freedom systems. Single degree of freedom systems means only one component. So there is one so there is mass is concentrated at one location, and only one component of motion of that mass is possible. Okay, so single degree of freedom system, one component of motion, it can be horizontal displacement or whatever, one component of motion is possible. The first single degree of freedom system is a one-story, one-bay frame. We are stipulating that the frame has a period of half a second, and damping is 2% of critical. The period, the damping, all those concepts we discussed early on. The second single degree of freedom system is a very similar frame, mass concentrated at the root level, and we are allowing only lateral translation of the mass. The mass can move right to left and nothing else. And the period of the second system is 1 second, and the damping is still 2% of critical. The third frame has a significantly longer 2-second period, and the damping is still 2%. Now, if we subject the base of this first frame to the north-south component of the 1940 L central ground motion, from structural dynamics, we can calculate the displacements at the roof level, the horizontal displacements, and that's what the displacement history looks like. Okay, it in a way reflects the accelerogram, but obviously it has a different signature. And the maximum displacement from that displacement history is 63 millimeters. Okay. The second frame, when subject to the same motion at the base, shows this history of roof displacements. It is now much more regular, and the period has lengthened, reflecting the period of the frame, and the maximum displacement is 168 millimeters. This frame, with a much longer period when subject to acceleration history at the base, shows this displacement history quite regular. The period is now long, reflecting the period of the frame, and the maximum displacement is now 225 millimeters. Okay. Here, in this example, the displacements have increased from half a second period to 1 second period to 2 second period, but it doesn't always have to be that way. They could have decreased and increased, or increased and decreased, whatever. Okay, you have to calculate them. Now, in this figure, we have plotted the 63 millimeter maximum displacement of the first system against this period of half a second. Half a second, 63 millimeter displacement. Then we have plotted the 1 second period of the second system and the corresponding 168 millimeter of displacement. We have also plotted the 2 second period of the third system and the corresponding 225 millimeter of displacement. Okay, so that gives us these points. Remember, we are plotting on the x-axis the period of the structure. This is 1 second, 2 second, 3 second. And on the y-axis, the maximum computed displacement at the roof level. The maximum displacement is also called spectral displacement. Those are identical things. Okay, the spectral displacement is the maximum displacement of a single degree of freedom system. I forgot to mention that all the systems are supposed to be elastic. They are supposed to remain elastic as they go through the earthquake ground motion. Since we are doing we are computing the displacements on the computer, there is nothing to prevent us from computing the spectral displacements at many other periods, not just half 1 and 2 second, and then drawing this kind of a curve. Okay? Join the points that we get, and that will give us a curve which is the displacement response spectrum. Okay, so this is the first time we are coming up with a response spectrum. You see the concept. This one is a deformation or displacement response spectrum. The response spectrum gives us the elastic responses of literally all the single degree of freedom systems in the universe. A response spectrum gives us the responses of all elastic single degree of freedom systems in the universe with varying periods but having the same amount of damping when subject to one component of one earthquake ground motion. Okay, so the response spectrum is for one component of one ground motion. It is for one fixed value of damping, but it is for varying periods. And it gives us the elastic responses of single degree of freedom systems. Quite a bit said, and everything I said is extremely important. The damping changes, you get a different response spectrum. The ground motion changes, you get a different response spectrum for the same elastic single degree of freedom systems. Okay. So this spectral displacement the same as maximum displacement. If we take our spectral displacement 63 millimeters at half a second period, we take 63 millimeters, divide by the half a second period, then multiply by 2 pi, 44/7 roughly. The quantity we get has the unit of velocity. If S sub d is in inches, S sub d over t will be in inches per second. That has the unit of velocity. And this quantity is very close to, but not the same as, the maximum velocity of the single degree of freedom systems. So this quantity is called spectral pseudo velocity. Okay, it is the term pseudo indicates that it is not quite equal to the maximum velocity, but typically it is pretty close. The word pseudo quite often is dropped. We would just say spectral velocity, meaning spectral pseudo velocity. There aren't two different things, spectral velocity and spectral pseudo velocity. They are one and the same thing. We quite often just simply do not say pseudo, but when we say spectral velocity, it is spectral pseudo velocity. The 2 pi over t is called circular frequency, omega. Okay. So the spectral pseudo velocity is the spectral displacement multiplied by the circular frequency, and okay, that's it. Then if we do with the spectral pseudo velocity, what we did with the spectral displacement, divide that by t, multiply by 2 pi, we get a quantity that has the unit of acceleration. It turns out that this quantity is very close to the acceleration of the single degree of freedom systems, but not quite the same. So we call this a spectral pseudo acceleration. Again, the term pseudo is more often than not dropped. We just say spectral acceleration, but we always mean this S sub a, as you see on the screen. It is 2 pi over t squared times the spectral displacement, or 2 pi over t times the spectral velocity, and 2 pi is omega, the circular frequency. Okay. So we saw the spectral displacement plot. Obviously, there is nothing to prevent us from plotting the spectral pseudo-velocities against the period, which we have done in the second figure. And in the third figure, we have plotted spectral pseudo-accelerations against the period. I absolutely want to emphasize that as we went from one slide to the next, the damping didn't change. We remained at 2% of critical, and the ground motion didn't change. We are talking about the north-south component of the 1940 El Centro motion. Okay, so we have obtained for that ground motion and for 2% of critical damping the displacement spectrum, the pseudo velocity spectrum, and the pseudo acceleration spectrum. Now, Professor Newmark, many years ago, came up with the idea of putting all three plots on the same piece of paper. So this can be done. Okay, so follow me closely. On this kind of a tripartite plot, as we call it, the period or the frequency is on the x-axis. Frequency is the reciprocal of the period. Newmark himself always plotted frequency on the x-axis. Here I have period on the x-axis. On the y-axis, it is always the spectral pseudo-velocity. On a few of these slides, the unit has not been changed. And I think it's okay for the purpose of our discussion. So x-axis has period on it, could be frequency. Y-axis has spectral pseudo-velocity, always on the tripartite plot. And then if period is on the x-axis, this diagonal scale from left to right gives you the spectral displacements. And this other diagonal scale from right to left gives you the spectral accelerations. Okay, this is 10 units of spectral acceleration, this is 100 units of spectral acceleration, and so forth. So if we take a point on the curve and go to the y-axis, we can read the spectral pseudo-velocity. If we drop a perpendicular to this axis, the diagonal axis, we can read the displacement. And if we drop a diagonal to the other if we drop a perpendicular to the other diagonal scale, we can read the spectral acceleration. So this one plot gives us all the information that we could obtain from the three different plots. Okay, this tripartite plot turned out to be quite important in the development of things even in building codes. Now, this is a plot directly taken from Professor Newmark's papers. So what he has done, so far we were plotting, first of all, the x-axis, because it is a Newmark plot, now has the frequencies on the x-axis, not the periods. On the y-axis, it is spectral pseudo-velocity, except that it has been normalized with respect to the maximum ground velocity. So on the y-axis, we have numbers. Okay. So spectral pseudo-velocity divided by the peak ground velocity. Yeah. The different curves are for 2% of critical damping, 5% of critical damping, 10%, no, the top one is 0. then 2%, then 5%, then 10%, then 20%, and 40% of critical damping, which is totally unrealistic in a structure. We are typically in the 2 to 10% range. The higher the damping, the lower the spectrum. Okay. Then what Professor Newmark has done is to indicate that the 5% damped spectrum, this is 0, this is 2, this one is 5%, the third one from the top. That spectrum, he indicates, can be approximated by the 3 red lines. Okay, so the 3-part red line is an approximation of the 5% damped spectrum. Since frequency is on the x-axis, now the right to left diagonal scale gives you the spectral accelerations can be read this way, okay, and the spectral displacements can be read this way. So I should have maybe, no, this is good enough. So this is spectral pseudo velocity on the x-axis. So this is the constant velocity part of the spectrum. Okay, this part at high frequencies or low periods is the constant acceleration part of the spectrum. Along this part of the spectrum, the spectral accelerations are constant. And at these low frequencies, high periods, it is the constant displacement part of the spectrum. The spectral displacements now are constant along that branch. Okay, you see on this diagonal scale where we are reading the spectral accelerations are normalized with respect to the peak ground acceleration. So the one important observation, in addition to the fact that the 5% damped spectrum can be represented by the 3 lines, is that along the constant acceleration part of the spectrum, the spectral acceleration is just about 2.5 times the peak ground acceleration. So this is a very important relationship that holds, like the plot is for 1940 El Centro north-south component, but this observation of Professor Newmark is across the board. The spectral acceleration along the constant acceleration part of the spectrum is 2.5 times the peak ground acceleration. And we will use that relationship all over the place. Also, along this constant velocity part of the spectrum, the spectral pseudo velocity is also just about 2.5 times the peak ground velocity. And these observations proved to be very, very useful. Okay. Now, if you go to this plot, the difference is period is on the x-axis, not the frequency. So the constant acceleration part of the spectrum will be here, the constant velocity there, and the constant displacement part of the spectrum will be to the right. You will see that. I think this will come up in discussion right now, actually. Okay, so we have gone from the Newmark plot to one of our plots where period is on the x-axis. The Spectral pseudovelocity is, as always, on the y-axis. Okay. So here we have shown the spectra still for the north-south component of 1940 L center ground motion. We have seen the spectra for 3 different amounts of damping. I believe it is for 2, 5, and 10% of critical damping. Okay. So because period is on the x-axis, this is now the displacement scale, not the, here, this was the acceleration scale. Now this is the displacement scale because period, not frequency, is on the x-axis. And this diagonal is the acceleration scale. I hope you see what I'm pointing to. Yeah. Anyway, so this plot is not very different from this plot, except we have only 3 amounts of damping, and I have period on the x-axis, not the frequency. Okay. Now, let me back off to this plot. These are response spectra for 3 different amounts of damping for 1 component of 1 ground motion. Does it make sense to use this spectra as the basis of design? And the answer is a resounding no. This entire field of earthquake engineering is full of uncertainties. If there is one certainty, it is that an earthquake that has come hit your structure in the past will never come hit it again in the future. A structure will never ever see the same earthquake twice. That being the case, it does not make any sense to design a structure for a particular response spectrum of a recorded earthquake. The smart thing to do is to collect the spectra of many earthquakes that have happened in the region in the past, and then take an average. That takes us towards a design spectrum. We then will start going from a response spectrum to a design spectrum. Now, only averaging is not going to do it either, because these distinct peaks and valleys that are characteristic of every response spectrum simply reflect the what's the word? What do I want to? It simply reflects how the particular ground motion affected this particular structure. If you hit the structure with another ground motion and look at the spectrum, there will be peaks and valleys, but at different locations, okay, at different periods. So those peaks and valleys don't have any significance for design either. Okay, those peaks and valleys are peculiar to the particular ground motion. Another ground motion will give us peaks and valleys somewhere else. So we smooth out those peaks and valleys. So from the response spectra in the previous picture, we go to smooth response spectra. This smoothing can be done on the computer, and there are decisions to be made. Do we want to be to have median values or median plus one standard deviation, and so on and so forth. But basically what we are doing is smoothing. We are smoothing out the peaks and the valleys. And then, as I said, we will take average. The smoothed average spectra would be fit to serve as design spectra. Okay, I hope I have been clear, and I want to emphasize that there is a huge difference between a response spectrum, which is for one particular ground motion, and a design spectrum, which is the product of averaging and smoothing of a number of response spectra for a number of ground motions. Okay. Now let us come to the middle curve. These are acceleration spectra, spectral acceleration on the y-axis, normalized with respect to the peak ground motion. These spectra were put together by Professor Harry Seed of Berkeley in the 70s at some point. I mentioned on another occasion that right now we are drowning in strong motion records. Anytime the earth shakes at any corner of the globe, we get all kinds of records from all kinds of sources. But back when Professor Seed did this work, there were roughly 30 accelerogram, strong motion accelegrams on rock, roughly 30 on what he calls stiff side conditions, not quite rock, another 30 or so on deep cohesionless soil, and just about 15 on soft to medium clay and sand. For those different soil conditions, rock, stiff side conditions, deep cohesionless soil, soft to medium clay and sand, he came up with smoothed average spectra, as you see in the figure. Okay. So these spectra, acceleration on the y-axis, because spectral acceleration, remember, is directly related to base shear, was adapted for building code use in the very important ATC3 document that I am sure I mentioned, ATC3, dated 1978, is pretty much the source of the modern seismic design we are doing today. This document, after modifications, became the first 1985 edition of the NERP provisions, National Earthquake Hazards Reduction Program provisions. That set of provisions was published or updated every 3 years under federal funding until 2009. So there was 98, 1988, 91, 94, 97, etc. until 2009, then 2015, and then 2020. So the 3-year cycle was discontinued after the 2009 edition. Actually, I don't remember if there was a 2006. Anyway, recent times it has been 6-year editions. And those documents are the source of seismic design provisions of ASCE 7 and the IBC. Now in ATC3, they decided to use Professor Seed's spectra as the basis of design, but they did a few things. The rock and stiff side conditions were combined into one, what they call soil type 1, rock and steep soil. The deep cohesionless soil remained soil type 2, and the soft is soil type 3. Okay? And they have, for design purposes, you see they have uh, changed the shapes somewhat because they thought that the altered shapes are more suitable for design. And very importantly, they have normalized the spectral acceleration not with respect to peak ground acceleration, but effective peak acceleration for steep side conditions. Effective peak acceleration for steep side conditions. What is effective peak acceleration? So that's where this top figure comes in. We have one of those tripartite spectra, spectral pseudovelocity on the y-axis and so forth. Okay, this is the constant acceleration part of the spectrum because we have period on the x-axis. This is the constant velocity part of the spectrum. This is the constant displacement part of the spectrum. The spectral pseudovelocity, the spectral acceleration divided by 2.5 will give us, remember, peak ground acceleration. Okay, so that is called effective peak acceleration. S sub A, the spectral acceleration, divided by the 2.5 from Newmark's work, gives us a spectral quantity that is close to the peak ground acceleration. It remains a spectral acceleration, but it is close to peak ground acceleration. So it is effective peak acceleration. And then the spectral pseudovelocity divided by 2.5 gives us, again, a spectral quantity that is close to the peak ground velocity. And we call that effective peak velocity. Okay, so ATC defined these terms, effective peak acceleration, effective peak velocity, and they actually produced maps of not the effective peak acceleration, but effective peak acceleration coefficient, as they called it. If effective peak acceleration is so much of g, let's say 0.4 g, the effective peak acceleration coefficient was the 0.4. And that was plotted in ATC3 for the entire country. When it comes to effective peak velocity, instead of plotting the effective peak velocity, they plotted a related acceleration coefficient, A sub v. A sub v is an acceleration coefficient related to the effective peak velocity. If effective peak velocity is 12 inches per second, EPV is 0.4. Okay, so all those details will not sink in, and that is probably unnecessary because this is in the past. But effective peak acceleration and effective peak velocity, I think you need to understand because if you go through literature, you will come across them. Effective peak acceleration is spectral acceleration divided by 2.5. It is a spectral quantity that is close to the peak ground acceleration. The effective peak velocity is the spectral pseudovelocity divided by 2.5. It is a spectral quantity that is close to the peak ground velocity. Okay, so these were the design spectra of the ATC3 document. ATC3 was followed by 1985, 1988 NERP provisions. In 1988, NERP very soft soil was added. So those are details for you. Now, the next thing that happened is the structural engineers of California for the 1988 UBC decided that the soft soil spectrum being lower than the other spectra is a little too fancy for engineering use. So they went with the same plateau for all three plots. So this is the design spectrum of the 1988 UBC. Spectral acceleration on the y-axis, normalized with respect to the effective P ground acceleration as the ATC3 spectrum. Okay, so 1988 UBC. The next significant thing that happened was in the 1994 NARP provisions. In the Mexico earthquake of 1985, and then in the Loma Prieta earthquake of 1989, and I have talked about this in one of the segments, we became very aware that the short period part of the spectrum, this part of the spectrum, and the long period part of the spectrum are amplified differently by soft soil overlying rock. Okay, so short period ground motion is amplified differently by overlying soft soils than is long period ground motion. So 1994 NARP provisions proposed that this part of the design spectrum, the constant acceleration part, be amplified by a site coefficient f sub a, short period site coefficient, acceleration related site coefficient, and that this part of the spectrum be amplified by a different site coefficient, a velocity related site coefficient, a long period site coefficient, f sub v. So this was the introduction of the two-part approach to local site response. This was a very major change. Okay, 94 NARP provisions. From that, we went to the 97 UBC design spectrum. 97 UBC was in effect in California until the last day of 2005. Now this is pretty recent, and it is in use in many parts of the world, that I can assure you. Yeah. So the 1997 UBC spectrum is not very different from what we had earlier, except that this two-factor approach had been introduced. So the plateau now is defined by 2.5 C sub A and the descending branch by C sub B over T. Okay. The C sub A is like F sub A times A sub A. And the C sub B is F sub B times A sub B. The 97 UBC spectrum is exactly this spectrum of 1994 NARP provisions. This F sub A times A sub A is being called C sub A, and the F sub B times A sub B is being called C sub B. That's all that has happened. Okay. And then coming closer to today, so 97 UBC, then we had 2000 IBC. This is the design spectrum in those codes. The flat top, the constant acceleration part of the spectrum, is defined by S sub ds, and the descending branch by S sub d1. So S sub ds is not the same as, but corresponds to 2.5 C sub A of the UBC, and the S sub d1 corresponds to the C sub B of the UBC. So let us pause here for a couple of a minute or so, because I have covered a whole lot of ground, decades of development. The first thing I try to emphasize is the huge difference between a response spectrum and a design spectrum. Design spectrum is the result of smoothing and averaging of a number of response spectra. The design spectra for code use originated from Professor Harry Seed's work in the 70s, which was adapted by ATC3 and then evolved in different editions of the NERP provisions until the 1988 UBC picked it up. Then it ended up in the building code. And then the big development was 1994 NERP provisions introducing the two-factor approach to local site conditions. And that was adopted by the 1997 UBC, and then IBC stayed with the same. Okay. Now from UBC to IBC, another huge change took place, and you know about it. I don't know. I want you to put the two together. The UBC spectrum corresponded to the design earthquake of the UBC, which had a 90% probability of non-exceedance in 50 years. Or this was, roughly speaking, the 500-year return period earthquake. Okay, so this spectrum corresponded to the 500-year return period earthquake. 97 NERP provisions abandoned that. In 97 NERP and in 2000 and 2003 IBC, and in all IBC editions since, we went from the basis of seismic design was changed from ensuring life safety in the 500-year return period earthquake to preventing collapse in the so-called maximum considered earthquake. Okay, I have discussed all of this, and I have that again on a couple of slides. But this profound change took place. So we are now designing for 2/3 of the maximum considered earthquake. Okay, that is in a way our design earthquake. So all these quantities S sub ds, S sub d1 are for 2/3 of the maximum considered earthquake. So the point I'm making is that while the UBC spectrum was for the 500-year return period earthquake, this spectrum is for 2/3 of the maximum considered earthquake of the NERP provisions, and the IBC. Okay, and we will revisit the definitions, but what I mentioned is very, very important, that the basis of design had changed in the meantime. So this is why this is a correspondence. This is not one is equal to the other, not at all. Okay. So this was 2000, 2003 IBC, then very close to our time ASC 705 design spectrum. This is your latest. Okay. No difference between the 2003 IBC and this spectrum, except that we have added so this is the constant acceleration part of the spectrum defined by S sub ds. This is the constant velocity part of the spectrum defined by S sub d1 over t. We have added the constant displacement part of the spectrum, okay, varying with 1 over t squared. And this portion starts at a period T sub L that is called the long period transition period in the IBs in AC7. In AC7, TL is mapped for the entire United States. In BNBC, T sub L has a fixed value of 2 seconds, as I mentioned repeatedly one of these days, and you will see that again. Okay, so in any case, so this spectrum evolving from the Harry-Seed spectra is the basis of design in ASC 705. Okay. So design earthquake ground motion prior to IBC is the 500-year return period ground motion, as I just mentioned. The ground motion today, we define maximum considered earthquake ground motion. In the source document and our provisions, this is the definition: maximum level of earthquake ground shaking that is considered reasonable to design buildings to resist. This, I pointed out, is not very useful as a definition because of the word reasonable in there. It is kind of declaration of principle. The definition that was built around that declaration of principle is that the maximum considered earthquake is the 2500-year return period earthquake, 2% probability of non-exceedance in 50 years. In certain parts of the world, including coastal California, where we know the seismic sources and the capabilities of the seismic sources, we consider the maximum considered earthquake to be the largest earthquake that can be delivered by the known seismic sources. This is called the deterministic earthquake. This is irrelevant for your purposes in Bangladesh. Okay, so forget about this part of the definition. So IBC design ground motion. The quantities that are mapped are the short period and the long period spectral accelerations corresponding to the maximum considered earthquake on site class B as defined in AC7 and the IBC. Site class B is soft rock, California rock that is not geologically very old. S sub S is the spectral ordinate at a period of 0.2 seconds, corresponding to the maximum considered earthquake on site class B. S sub 1 is the spectral acceleration at a period of 1 second, also corresponding to the maximum considered earthquake on site class B. We multiply S sub S by the F sub A that we introduced, the short period site coefficient, obtaining S sub MS, soil modified short period ground motion parameter. This is also for the maximum considered earthquake. The difference between S sub S and S sub MS is S sub S is for site class B, S sub MS is for your particular site class. We likewise multiply S sub 1 by F sub V, the velocity related acceleration site coefficient, obtaining S sub M1, soil modified long period ground motion parameter. Difference between S sub 1 and S sub M1 is S sub 1 is for site class B, S sub M1 is for your particular site class. Both are for maximum considered earthquake. Okay. In design, we design for 2/3 of the soil modified MCE quantities. S sub ds is 2/3 of S sub ms, and S sub d1 is 2/3 of S sub d1 is 2/3 of S sub m1. All of this I have gone through with you on at least one previous occasion. BNBC gives you directly in the code S sub ds and S sub d1 values for different soil types, as they're called in BNBC, and for the different seismic zones. Okay, so if you are zone 2 Dhaka and your soil type is SD, your S sub ds is 0.45, directly given in the code. And your S sub D1 also directly given in the code is 0.36, very convenient. Those values are given. With that, you can construct your design spectrum. The other point I made, I don't remember which day now, is when we do the equivalent lateral force procedure, we modify our this spectrum, our elastic design spectrum, in 4 different ways. We eliminate the ramp building up to the flat top. We extend the flat top all the way back to 0 period. We lower the spectrum by the response modification factor R, and the same time raise it by the importance factor I. So that is the R over I definition. And then at the long period end, when 1 over T or 1 over T squared would give us very low design base shears, we impose minimum design base shears. There is a minimum design base shear that is independent of the seismic design category, 0.44 S sub ds times I times W. That would be very low when S sub ds is low, but we don't allow it to go any lower than 1% of the weight. And there is a minimum that applies where the long period mapped quantity is larger than or equal to 60% of G. This is rough equivalent of old UBC seismic zone 4. In those parts, we have a second minimum on the design base shear. And when both minimum values apply, the higher minimum controls. I have gone through all of this. So the V minimum is given by this expression, but never less than 1% of weight. And the other minimum is a function of R and is given by this expression. In BNBC, the spectrum is defined by these points T sub B, T sub C, and T sub D. T sub D, I have mentioned, has a fixed value of 2 seconds. T sub C is the same as T sub S of AC7. It is S sub D1 over S sub DS. The T sub B is not the same as T sub 0 of AC7. It is different, and I don't exactly know how T sub B was derived. But in any case, it defines the spectrum, and the values of T sub A, T sub B, T sub C are given to you in this table of in BNBC. So if you know your seismic zone and your soil type, then everything comes directly out of the code. You can draw your design spectrum. Your S sub ds is given, your S sub d1 is given, and these transition points are given, and your soil factor is also given. BNBC has stayed with one soil factor instead of going to F sub A, F sub B, like AC7. Although in Appendix C, I pointed out that it uses F sub A, F sub B, but F sub B is not an independent thing. Okay, so all those details I covered already. So this would be the spectra of BNBC that you can use in design. Okay, that brings me to a different phase of the presentation. So this is a very good time for a break. It's 27 after pretty much. So I'll come back at 32 after and try to go the rest of the way. Okay, it's time. So I will continue. So far we were talking about single degree of freedom systems. It's not a whole lot of practical structures that you can idealize as single degree of freedom systems. So we need to talk about multi-degree of freedom systems where there are multiple masses and the masses themselves may undergo not just one component of motion, but maybe translation into orthogonal directions as well as rotation about a vertical axis, for instance. Anyway, when we model a multi-story building, the simplest models are called lumped mass models, where the masses are lumped at the floor levels. So if we are modeling a three-story building as in this picture, we will assume the mass is concentrated at the two floor levels and the roof level, and that will give us three lumped masses. And if we further assume that those masses are allowed to move only in the left to right direction, that there is no perpendicular movement possible or rotation, then we have a 3-degree of freedom system, as many degrees of freedom as there are stories in the building. So that would be the simplest representation of a multi-story building that can still give us acceptable results. So this is the lumped mass model of a 3-story building that is undergoing vibrations under earthquake excitation. The thing that is all important is that the deformed shape of the building changes from one instant to the next. Okay, the deformed shape is not the same for any significant length of time. While that is true, it is possible to deform this three-mass model into three different shapes if we can very carefully deform the frame into one of the shapes depicted in the three pictures and then let go. The building will keep on vibrating without changing its shape. Okay, if we were to carefully deform this model into that shape and then let go, it will go on vibrating without any change of shape. And those natural shapes are called the natural modes of vibration. Natural meaning they are properties of the structure. Okay? Natural modes of vibration. For a 3-degree of freedom system, we have 3 natural modes of vibration. Importantly, as long as everything is elastic, the actual deformed shape can be a linear combination of the mode shapes, and this is what is expressed here. Okay, let's go into the details. So the displacement here x1 at level 1 is the phi 11, which is from the position of rest to the extreme curve. Okay, that's P11. That is the modal ordinate, if you're the mode shape ordinate. So x1, this displacement is P11 times a multiplier plus P12 times a multiplier plus P13 times a multiplier. X2, the displacement at level 2, likewise is P21, okay? The modal amplitude at the second floor level when it is the first mode deformation, phi21, multiplied by the same x1 as before, phi22 multiplied now by the same x2 as before, and phi23 multiplied by the same x3 as before. Similarly, x3 can be expressed as phi31 times x1, phi32 times x2 plus phi33 times x3. So that is kind of important way of looking at how a multi-degree of freedom system deforms. So we can write this in matrix notation. The vector of the actual displacements is the mode shape matrix multiplied by the vector of those multipliers, which are called generalized coordinates, whatever the multipliers, the capital X's. Okay. So the vector of the actual displacements is the mode shape matrix multiplied by the vector of the multipliers x, the generalized coordinates, and the most shorthand version is the vector of displacements is the mode shape matrix multiplied by the vector of the generalized coordinates, the mode shape vectors. When the multi-degree of freedom systems vibrates in one of its natural modes, this is what the vibration looks like. It is exactly like that of a single degree of freedom system. Okay. It has a regular period of vibration. That would be the modal period, T sub m, and the magnitude dies down because of damping. Okay, in this case, it will be modal damping. Now, let us get down to numbers. Otherwise, I don't think anything really registers. So we will do this 1 by 3-story frame. This is the largest that can be done by hand, I think. So we took, again, the numbers were round in American units. When we converted, they're not round anymore, be that as it may. So the story height is 30-50 millimeters. The weight at every floor level is 17-19 kilonewton per floor. The E is 27,579 MPa. That kind of tells you it's a concrete frame. And I of each column is 1.87 e to the power 9 millimeter to the power 4. And that is 70% of I gross. That's how we calculated it. Okay. So H sub S, W, E, and I column. The mass is weight divided by the acceleration due to gravity Weight is given as 1719 kilonewton. The G is 9810 millimeter per second squared. Anyway, mass comes out to 175,000 kilograms. The mass matrix for a lumped mass model, the mass matrix is a diagonal matrix with only the diagonal term having values. The off diagonal terms are 0. Okay? So the mass matrix has 175,000 here, 175,000 here, mass, and 175,000 mass at level 1. So we can take 175,000 out. So this is what our mass matrix looks like. The stiffness matrix, this is the tough part. When we do these things on the computer, putting together the stiffness matrix is where the actual work is done. Okay. This is tedious and a lot of work. Okay, so 12vi over height cubed is 44 kilonewton per millimeters, which is 44 million Newton per meter. The units are very tough for me. They hopefully will make sense to you. I don't know. Anyway, Kij, stiffness coefficient, is force corresponding to coordinate I, resulting from a unit displacement of coordinate j. If we apply a unit displacement at coordinate j, what is the force at coordinate I? That is Kij. So the numbers are, this is our coordinate 1, this is coordinate 2, this is coordinate 3. That's how we numbered the floors. Remember, 1, 2, and 3. So here we have imparted unit displacement to coordinate 3. So the second subscript is always 3 in all 3 coefficients. The force required at coordinate 3 is 44 units million Newton per meters, whatever. The force needed or induced at coordinate 2 is negative 44, and the force at coordinate 3 is 0. If we impart unit displacement to coordinate 2, we will need a force of 88 units. There will be negative 44 at the top, negative 44 at the bottom. If we impart unit displacement to coordinate 1, we will need 88 there, minus 44 at the upper level, and then nothing at the top level. So these numbers we can assemble into a stiffness matrix. K11. So if we take 44 out, K11 would be 2, that is here. K12 will be negative 1, which is here. K13 is 0, which is there. Okay. K21 negative 44 is here. K22 of 88 is here. And K33 of negative 44 is here. So this is how we assemble the stiffness matrix. Here it looks simple, only translation, only 3 numbers. But if you imagine 3 degrees of freedom per floor and 40 different floors and complicated configuration, assembling the stiffness matrix is a huge undertaking. Okay. Then equations of motion of multi-degree of freedom systems. Mass times acceleration. Mass is a matrix, acceleration is a vector. Damping matrix times the velocity vector. Stiffness matrix times the displacement vector is equal to the vector of applied forces that cause the vibration. If it is undamped free vibration, undamped means the C matrix is a null matrix and the vector of forces is a null vector. The vibration is taking place without any forces being applied. It is because of earthquake excitation, for instance. Then the equations of motion get reduced to mass matrix times acceleration vector for plus stiffness matrix times the velocity vector is equal to the null vector. Okay. Now we say motion of a system in free vibration is simple harmonic. Okay. That may be restricted to undamped systems. I am not sure, but a system in free vibration shows simple harmonic motion, meaning the displacement can be expressed as an amplitude times sine of omega t. It is a sine function of time. That's what simple harmonic motion means. So the x can be written as a amplitude times sine of omega t. If we take first differential of that, we'll get omega a cosine of omega t. And if we take a second differential, which will give us acceleration, that would be minus omega squared a sine of omega t. So differential of sine is cosine, differential of cosine is negative sine. Okay, we get the sine back. So so this is our equation, m times acceleration vector plus stiffness matrix times the displacement vector is the null vector. If we substitute for the accelerations and the displacements are k times a, the accelerations are negative m times a. Negative. So the acceleration is negative omega squared times a, and the displacement is a, because the sine omega t, since the right hand side is 0, the sine omega t does not have any significance. So if we rewrite it, k minus omega squared m, this is a matrix, times the vector of amplitudes is equal to the null vector. Okay. So this matrix, k minus omega squared m, in our particular case, we know the stiffness matrix, we know the mass matrix. Our stiffness matrix had 88 units here, and the mass matrix had 175. So k minus omega squared m would be this. Here we had a mass and a stiffness, but here we had no mass. It is just the stiffness. Here it is just the stiffness. Anyway, if you go back to our stiffness matrix and our mass matrix, you will see that we have written here the stiffness, the k minus omega squared m term. Okay. It's I don't want to go back and forth. It takes time and may even be confusing, but that's precisely what we have done. We have our k matrix, we have our m matrix. We are assembling the k minus omega squared m matrix. Okay. This matrix times the amplitudes is equal to the null vector. If we take the determinant of that matrix and set it equal to 0, we can solve for values of omega. Since there are 3 equations, there are 3 values of omega that we will get. So if we set the determinant of this k minus omega squared m matrix equal to 0, we can solve for 3 values of omega, which we did, and the omega values came out as shown here. And since period is 2 pi over omega, the modal periods came out to 893 seconds for the first mode, 319 seconds for the second mode, 221 seconds for the third mode. Okay. The first mode period, also called the fundamental mode, is always the longest, and it gets shorter as we go to the higher mode shapes. One thing I should have pointed out, very fundamental, the first mode never crosses the zero axis. Okay, all the masses move in the same direction. In the second mode, there is one crossing of the zero axis. Okay, so at the top, the masses are moving in an opposite to that, the motion of the masses in the lower portion of the structure. Third mode has 2 zero crossings, and so on and so forth. If we have 100 modes, the 100th mode will have 99 zero crossings. Okay, now if we go back to our equation, the equation being k minus, this is our equation. If we go back to this equation, this is our k minus omega squared m matrix, except here we have written omega 1 for omega. Okay, the circular frequency of the first mode. Then our amplitude matrix would be the matrix of the mode shape, the first mode shape, phi 312111. And by solving this set of equations, the right-hand side is a null vector. We can figure out phi 3121 and 11. Phi 31 is 1, 21 is 802, 11 is 445. So those three numbers define the first mode shape. Okay. If we write omega sub 2 for omega in the previous equation, now it will be the second mode shape, and the second mode shape comes out to the numbers that are shown, and the second mode shape crosses the zero axis once, as we know. So 32 is 1, 22 is negative 5512 is negative 1.22. We always make the top value equal to 1, and then the others are relative values, because we are interested in the shape. The magnitude is in the multiplier, remember the x. If in the equation, in the matrix, we write omega equal to omega 3, this will be the mode shape vector of the third mode, and the third mode was obtained as these values. The top is 1, this is negative 2 and a quarter, this is plus 1.802. Okay, now AC7 tells you a whole lot of things. BNBC is a little more reticent. It doesn't have a lot to say. And I don't think I will read this stuff, but let us see. A 5% damped elastic design response spectrum constructed in accordance with figure 1141 using the values S sub ds and S sub d1 consistent with the specific site. Okay? So the design spectrum of AC7 is the spectrum given in figure 11.4-1, the spectrum that we saw, using the values of S sub ds and S sub d1 for the particular site. Okay, which will come, we will read S sub S and S sub 1 from the maps, or go to the USGS website, whatever. You will multiply S sub S by F sub A, multiply S sub 1 by F sub B. Then you will take 2/3 of those quantities to get the design quantities, S sub DS and S sub D1. So that spectrum can be used as the ground motion input for modal response spectrum analysis. Or in your case, you can use the BNBC spectrum or whatever. There can be site-specific spectrum, but you have to have a spectrum. If you want to do modal response spectrum analysis, the earthquake input, what the earthquake is feeding into the structure, will come from the spectrum. So site-specific spectrum, there are things, very important things said in ASC 7 that I included here, but I'm not going to read because this is a lot of writing, and some of the stuff may sound a little bit strange to you, but it talks about the site-specific analysis that ASC 7 would have us do. And when you establish a spectrum by site-specific analysis, what would be your spectral acceleration, S sub A? Okay? And how would you figure out your S sub DS and S sub D1? All of that is said in these pages that I'm not going through. Structural modeling. Some of this I think I covered on a previous occasion. A mathematical model of the structure shall be constructed for the purpose of determining member forces and structure displacements resulting from applied loads and any imposed displacements of P delta effects. The model shall include the stiffness and strength of elements that are significant to the distribution of forces and deformations in the structure. So everything that contributes significantly to stiffness shall be modeled. It can be a non-structural element, you still have to model it, and represent the spatial distribution of mass and stiffness throughout the structure. So if you have a swimming pool at the top of your structure, you better have a big mass to represent the swimming pool. Okay, the spatial distribution of mass and stiffness must be represented in this mathematical model. Then it talks about details of when you need 3D analysis, and then the model shall comply with the following. Stiffness properties of concrete and masonry elements shall include the effects of cracked sections. This is very specifically said. You cannot go with just gross section properties. For steel moment frame systems, the contribution of panel zone deformations to overall story drift shall be included. The next thing, let me, maybe I was wondering if I should read it or, yeah, okay. So an elastic dynamic analysis of structure utilizing the peak dynamic response of all modes having a significant contribution to total structural response. That is kind of definition of modal response spectrum analysis. An elastic dynamic analysis of structure utilizing the peak dynamic response of all modes. This is important. In modal response spectrum analysis, we are concerned only about the peak response of the various modes, not the history of response. Okay? Our sole preoccupation is with maximum values. So modal response spectrum analysis is an elastic dynamic analysis of structure utilizing the peak dynamic response of all modes having a significant contribution to the total structural response. So 100-story building has 100 modes, but the 100 modes, all 100 modes do not contribute significantly to structural response. It will be only the first few modes, I don't know, maybe the first 10. Those are the ones we consider. Okay, and then how many to consider is specified. We will come to that. Peak modal responses are calculated using the ordinates of the appropriate response spectrum curve, which correspond to the modal periods. Okay, so you have modal periods. You go to your spectrum, and you see the response quantity. Spectral acceleration, spectral velocity, whatever. Maximum modal contributions are combined in a statistical manner. So this is another very important thing. The first mode will not hit its peak at precisely the same instant that the second mode hits its peak. So these modal maxima don't occur all at the same time. So we cannot just add the modal maxima. If we do, it will be an overestimate of response. So we take a statistical sum of the modal maxima, typically a square root of the sum of the squares. But if the modal periods are close together, then we have to go to more complicated sums, the quadratic, what is it, CQC, anyway, complete quadratic combination, whatever. There are more complicated statistical sums that are available. Okay, then we are doing all of this, but we don't want to cut our ties to the equivalent lateral force procedure. Somehow we have a lot of confidence in it. So we say if the dynamic base shear, the statistical sum of the modal base shears, is below 85% of the equivalent lateral force base shear, you shall scale up all modal quantities by the ratio between 85% of equivalent static base shear and the dynamic base shear. Let us say the dynamic base shear is 100, 85% of the static base shear is 135. So you will amplify all response quantities by the factor of 1.35. That is the scaling that we are talking about. Okay. The equivalent lateral force procedure base shear should be computed using a period that should be based on rationally computed period, except that it cannot be taken any larger than C sub u times T sub A. Remember, C sub u in Bangladesh is 1.4, T sub A is the approximate period. Very importantly, there is no scale down of the dynamic base shear. If the dynamic is high compared to the static, you cannot scale it down. There was a time when we used to do it, but no more. And then the R over I modification remains. We do not do elastic design. We do not design our structure for elastic response to the design earthquake when we do dynamic analysis. So we will still lower the spectrum by R and amplify it by I. That doesn't go away. Okay, I have broken down modal response spectrum analysis into steps 1 through, I don't remember now, and I am not going to read them. These are, I have reread them, made little modifications. I think you will find these steps to be extremely useful. But I think instead of reading the steps, we will just implement them in this example that we started. and that probably gives you the best feeling that I can give you for what it is that is involved. Okay, so the same structure, nothing has changed, same quantities. This is a repeat. We assemble the mass matrix, we assemble the stiffness matrix, then we assemble the K minus omega squared M matrix. Okay, these are all steps. By writing omega equal to omega sub 1 in the K minus omega squared M matrix. No, before that, by setting the determinant of that matrix equal to 0, we obtained 3 modal periods or 3 modal circular frequencies. And these values are at the top of this slide and the next 2 slides. So this is obtained by setting the determinant of the K minus omega squared M matrix to 0. Now in this calculation, we have written the K minus omega squared M matrix with omega equal to omega sub 1. Then the matrix of amplitudes becomes the first mode shape vector. When we solve these equations, this matrix times this vector equal to null vector, we get the first mode shape as shown here. Okay. So P31, P21, P11 defines for us the shape of the first mode. By writing omega equal to omega sub 2 in this matrix, we get the second mode shape vector, and that came out to these numbers. And these are still repeats of what I have already shared with you. By writing omega equal to omega sub 3, we get the third mode shape vector, which comes out to the numbers that you see here. Okay. From this point on, we are doing something additional. Now, these the problem with skipping the steps is I don't remember ever the names of these quantities. The L's are called one second, be patient with me, please. The L's are called earthquake participation factor and the M's are modal mass. Okay, earthquake participation factor, I can never remember that, and modal mass. Then effective weight and participating mass. So once we have our mode shapes, we will calculate the L and the M. I already forgot participating something, and the modal mass for each of our 3 modes. Okay, the L is summation of the weight at a level multiplied by the mode shape amplitude at that level, and that quantity is summed over all the levels. The difference between L and M is here. The mode shape, the mode shape ordinate is squared. Okay, so the W sub I in our case is fixed. It's the same at every level, 175,000 kilograms. So we can take it out. Summation of phi I1 over the three levels would be P11 plus P21 plus P31. We calculated these numbers. They're just 2 pages up. Phi11 is 445, P21 is 802, P31 is 1. So 445, 802, 1, that gives us 393 million. And the modal mass is P11 squared, P21 squared, P31 squared. That comes to 322 million kilograms. For the second mode, it is the second mode shape, and the second mode shape was determined. Those are the numbers. So this is our L for the second mode. This is our M for the second mode. This is negative 135 million. This is positive 488 million. For the third mode, this is the third mode shape, the third mode shape squared. This number comes to 96,600, and that number to what is it? Whatever. Big number. Okay. Now, based on the L's and the M's, we calculate the effective weight in the various modes. So effective weight in the first mode is given by this expression. Effective weight in the second mode is given by that expression. Effective weight in the third mode is given by that expression. Okay. L sub 1 we calculated, M sub 1 we calculated, G is 9.81 whatever units. So the effective weight in the first mode comes out to 4707 kilonewtons. Effective weight in the second mode 365 kilonewtons, and effective weight in the third mode to 56 kilonewtons. Okay, these are calculated values. The participating mass is the effective weight divided by the total weight. Okay, our total weight, it was given 1700, and we have to go all the way back 1798 or something in the problem statement. It may be worth it here. 1719 per floor. So 3 times that would be the total weight, 5157, right? 3 times 17 is 51, 3 times 19 is 57, 5157 kilograms is the total weight. Okay, so 51, 57 has become 56 somehow. Okay, so the effective weight, first mode effective weight 4707 divided by 5156 is 91.4. The effective weight of the second mode divided by the total weight is 7.1%. And effective weight of the third mode divided by the total weight is 1.1%. So basically, this is not refined, this is kind of crude, but basically what this says is 91.4% of the mass of the structure is vibrating in the first mode, 7.1% in the second mode, and 1.1% in the third mode. Okay, that's basically what we are getting. ASCE 7 says as long as you have captured 90% of the modal mass, that's as many modes as you need to consider. Here, the first mode itself accounts for more than 90% of the modal mass. So all we need to consider is the first mode. But we carried all 3 modes, but technically, according to ASCE 7, At this stage, we could drop the second and the third mode and proceed with only the first mode. Okay. So this participating mass in our case is 996. The first three modes capture 996. Obviously, it should be 1.0. That is a little bit of round off. We have nothing else, just the three modes. But importantly, the first mode accounts for 91.4% of the participating mass. So consideration of modes 1, 2, and 3 is sufficient. Indeed, the consideration of just the first mode would have been sufficient because the participating mass of the first mode is more than 90%. Now we are trying to calculate the modal base shears. Base shear comes from, base shear is, remember, C sub S times the seismic weight. And C sub S is S sub A, the spectral acceleration multiplied by I divided by R. This should have been I. The sub E came in as C710. We didn't find any way. Well, it wasn't easy to remove the E's, so they have remained on the slide. So you might want on your note to delete the E. Anyway, so modal base shear coefficient is modal spectral acceleration multiplied by I by R. The modal spectral acceleration, if we go with the AC7 spectrum, would be, remember, the descending branch is S sub D1 divided by RT, and the flat top is S sub ds over R. Okay, so the spectral acceleration would be S sub D1, I over R is always there, divided by T. We will use the modal period to find the modal base shear or the modal response coefficient. And then that comes in our case to S sub D1 is 0.6. The G has to be inserted because that is a coefficient. We need an acceleration. So the S sub D1 is actually 60% of G. I is 1, R is 8. We are doing a special moment frame, and T sub M. So modal base shear coefficient is 0.75 divided by modal period times G, but it cannot be any larger than S sub ds of 1, I is 1, and R is 8. Okay, so it cannot be any larger than 100.125, 12.5% of G. So we are doing this example for a location where S sub ds is equal to 1 and S sub d1 is equal to 0.6. I should have mentioned it. It probably was on an earlier slide and I missed it. So we are using the AC7 spectrum. Our S sub ds value is 1.0. Our S sub d1 value is 0.6. So that tells us that it is a high seismic area. So we have to use special moment frames that will make R is equal to 8. So hopefully this is pretty clear. Modal base shear coefficient is given by this expression, except that it cannot exceed that much. We have modal periods. First mode period 893 seconds. So first mode base shear coefficient is 0.75G divided by the modal period, which is 0.840G. Second mode period is so much. So second mode base shear coefficient is 0.75G divided by the period, which is that, but it cannot be any larger than 0.125G. So use 0.125G for the second mode base shear coefficient. For the third mode, the period is so much. So 0.75G over period is 3394G, which being larger than 125G, we use 125G. The modal base shear is the modal base shear coefficient that we calculated divided by the modal mass divided by G. The G is you have to keep track of, and I don't have that time to spend, but trust me, where we have placed the G's need to be there. So the V sub 1 comes to 0.840 is the coefficient that we calculated here, and the modal mass is 4707 calculated value. So 395 kilonewtons. The second mode base shear 0.125 times the modal mass 46 kilonewtons, and the third mode base shear 7 kilonewtons. The dynamic base shear, as it is called, the square root of the sum of the squares of the three, comes to 398 kilonewtons. Okay, we now have to figure out if it is smaller than 85% of the static base shear. Okay. So this is our dynamic base shear, square root of the sum of the squares of the modal base shears. The static base shear is given by this formula that you are all familiar with, subject to a maximum of that and a minimum, which is this, and a near fault minimum, which is that. Okay, you are all familiar with this equation. We start with T sub A, the C sub T for a moment frame of concrete is 0.16. In that unit may be our unit that we may have forgotten to convert. Maybe, yeah, that is the number. So that number is wrong. Circle it or something. So your coefficient is 0.466 and the power is 0.9. The height is 9.14 meters. So that was given in the problem statement. So the approximate period is 342 seconds. We will go with 1.4 times the approximate period, which is 479 seconds. You should not do that without calculating rational period, which we actually did. And the rationally computed period was much higher than 1.4 times T sub A. And this is why we went with 1.4 T sub A. Without calculating rational period, you cannot just jump there. Okay. So based on that period, C sub U, T sub A, the static base shear comes to 157W by that formula. The upper bound is 125W, so that governs. The minimums do not govern. Okay, so our static base shear is 0.125 times the 5157 number, which is 645 kilonewtons. So we have 645 kilonewtons of static base shear. 85% of that is 547. Our dynamic base shear is 398. Which is less than 85% of static. So everything has to be scaled up by the 547 divided by 398, which number comes to 1.375. Okay, so once again, the dynamic base shear of 398 is smaller than 85% of static, which is 547. So the modal base shears that we calculated have to be scaled up by the ratio between 547 and 398, which is 1.375. So first mode base shear of 395 is now 542.7 after the scale up. Second mode base shear of 46 is scaled up to 62.7. Third mode base shear of 7 is scaled up to 9.7. So the square root of the sum of the squares is now exactly equal to 85% of the static base shear. Okay. So those are our adjusted modal base shears. Now we will distribute this. Please follow me very closely. So we have first mode base shear of 542.7 kilonewtons, and the modal period, it is not written here. We know the modal period. I may have to go anyway. The 542.7 kilonewtons of first mode base shear is distributed along the height of the structure according to this equation. Okay, so the I I don't know how else to say it. So essentially the first mode base shear is distributed along the height of the structure according to the first mode shape. That's the best way to say it. The first mode base shear of 542.7 kilonewtons is distributed along the height of the structure according to the first mode shape. And that's what we are trying to express by this expression. The second mode base shear will be distributed along the height of the structure according to the second mode shape, and the third mode base shear will be distributed along the height of the structure according to the third mode shape. Okay, so the first mode base shear of 542.7 kilonewtons distributed along the height of the structure according to the first mode shape gave us those forces at the three floor levels, the two floor levels and the roof level. The addition of the three is 542.7. The second mode base shear distributed along the height of the structure according to the second mode shape gave us those forces at the three floor levels. Remember, second mode means 1-0 crossing. So at the first level, the second level, the masses are going in one direction. The third level, the masses are going in the opposite direction. And the sum of the three forces is the second mode base shear of 62.7 kilonewtons. The third mode base shear distributed along the height of the structure according to the third mode shape give us those forces at the three floor levels. There are now 2 zero crossings. We go from positive to negative back to positive. And the sum of the three is the 9.8 kilonewtons of modal base shear. Okay. So this is to more or less to scale what we have established. So the structure is simultaneously vibrating in three modes. I want you to understand that. The first mode vibration, second mode vibration, third mode vibration, all of that is happening at the same time. The first mode vibration imposes those forces at the three floor levels. The second mode vibration imposes those forces at the various floor levels, and the third mode vibration imposes those forces. Okay. how we want eventually to figure out the earthquake-induced bending moments, shear forces, axial forces at the various critical sections of the various structural members. How do we do that? Can we take square root of the sum of the squares of those floor level forces and apply that on the structure and do an analysis, and that will give us what we need? The answer is no. If we combine these forces, the floor level forces, we will lose the signs. As soon as you square something, the sign is lost. So the fact that this is directed this way and that is directed this way will be lost. And that is vital to calculating properly what we need to calculate. So the only way to go, there is no shortcut. You have to analyze the structure under the first mode forces. You have to do a second analysis of the structure under the second mode forces. You have to do a third analysis of the structure under the third mode forces. And then take square root of the sum of the squares of the bending moment at a support section, or the shear force at the end of a column, or the axial force in a column. So those response quantities will be statistically combined from the results of the three modal analysis. Okay, there is absolutely no shortcut to that I'm aware of. Okay, so we are once again pretty much on time. I really hope that these numbers will help you, will give you a feel for what it is that is done on the computer. And this feel to me is all important. Okay, without the numbers, you simply do not get that. There is no other way of getting it. Okay. Now, because those are metric numbers, I personally don't have, I don't relate to the numbers, but I thought it was better to convert to metric for your purposes. And if you want the original numbers, we can provide those also. I don't know that will help you any. Okay, thank you very much, and I'm open to questions.
I responded to most of the questions today,
Okay.
but I still left a few at the end, just for you. Yeah, today's session was kind of in my domain, so.
Oh, your domain. I see. Okay, good.
So, yeah, so I will start with the questions from the end. So, if the dynamic base shear is larger than the base shear, I think he's talking from the equivalent, that
Static.
ELF method,
The
static
static.
method.
Yeah, yeah.
We scale down.
No, I said specifically that you cannot scale down. Absolutely not. That is gone. That was a long time ago that we used to be able to scale down. We have to design for the higher values.
Okay, and then why software calculated period is sometimes so much higher than the approximate period?
That is pretty much by design. Approximate period, the reason is that the base shear is proportional to the reciprocal of the period. So the shorter the period, the larger the base shear. So we want the approximate period to be smaller than, quote unquote, the real period of the structure, so that if you don't later refine your period computation, if you don't later do rational period computation and modifying your original period estimate, you will still be on the conservative side. Okay? If we took the approximate period to be too long, then we might be unconservative. So that part is by design. Now, if it is very, very much longer than approximate, then there is something strange with your stiffness assumption. You have taken very low stiffness for some reason, and that would account for very long periods. So I don't know how much longer you are talking about, but the rationally computed period will be longer than approximate. I think in my entire life I have seen one exception to that. So it's basically always longer. But if it is, way longer, then your stiffness assumptions probably should be looked at.
For drift and torsional irregularity check, should we use the RSA or the ELF?
I didn't catch the beginning at all.
For drift and torsional irregularity check, should we use the RSA, that responsive trim analysis, or equivalent lateral force method?
I don't understand. Well, first of all, if you do modal response spectrum analysis, you will still have to do a drift check. The drift quantities will also be square root of the sum of the squares of modal drifts. Now, there is no scaling of drift. Only this is something important. I probably should have mentioned this. Only the force related quantities are scaled. The drifts are not scaled. So when the modal, the dynamic base shear is less than 85% of static, we scale up the bending moment, shear forces, axial forces. We do not scale up the drift related quantities. Anyway, we will take square root of the sum of the squares, and that will have to be within the limits that are given in ASCE 7. If there is torsional irregularity in the structure, then we have to consider torsion also has to be considered, the accidental torsion that we consider in static analysis has to be considered in dynamic analysis. That does not go away. If you have torsional irregularity, then the torsional amplification factor comes into the picture. The inherent torsion and the accidental torsion have to be amplified by the torsional amplification factor, and that amplified torsion has to be accounted for in the analysis. So it gets complicated, and sometimes we would consider torsion only in the first mode and not in the higher modes. I am definitely not the most competent individual to tell you how to do it, how to include torsion in the analysis, particularly in the higher modes, but it is supposed to be done. That much I can tell you. So it is not that you need to check drift, you figure out whether to do static analysis or modal response spectrum. It is the other way around. You make a decision based on whatever that your design shall be based on modal response spectrum analysis, probably because you have a tall structure and an irregular structure. And then you will have to do drift check as always, and you will also have to account for torsional irregularities if there are any.
I think he got answered. So the next question is, in between modal analysis and time history analysis, which will give much better or accurate results? Which analysis do you suggest?
I actually said this. Elastic time history analysis does not give you any more information than modal response spectrum analysis, as far as I'm concerned. You may get more numbers, but no new knowledge of significance. Inelastic response history analysis is the most accurate analysis that tells you how your structure will behave. However, the results of nonlinear analysis is as good as your ability to model the inelastic behavior of the regions that will go inelastic in the earthquake. So if it is a beam hinging region, you have to model it. If it is I don't know, if you are allowing a region in a column to go inelastic, that will be much more difficult to model. But whatever you are allowing to go inelastic in your time history analysis, the inelastic response of that portion of the structural member has to be properly modeled, and the modeling has to be based on actual testing. And so if your model is close to reality, then nonlinear time history analysis gives you the most accurate results that you can get.
What is energy response spectra and how can it be utilized?
Energy response spectrum is, I don't know how it is utilized. I think it is my I always thought it is for basically non-structural purposes. I do not know. The answer is I do not know, frankly. And there are different measures of energy. There are so many spectra that are used. And I no, this answer I do not know the answer. This question I do not know the answer to.
Okay. When should we use the CQC, complete quadratic combination, and when SRSS?
Yeah, when the modal periods are close together, the SRSS tends to give you inaccurate results. Then you switch to something like CQC. How close is close? There are guidances available in the literature. I cannot tell you without checking, but you can find that information.
Yeah, CQC will consider the correlation between different modes. So if you want to consider correlations, then CQC is the method to go. We should consider stiffness modifier. Okay, let me rephrase this, Dr. Ghosh. Should we consider stiffness modifier only when response spectrum analysis is required, or else, the basic question is that should we use the crack section properties only when dynamic analysis is required, or every
No,
time?
no. The modeling section applies to static as well as dynamic analysis. No, this is very basic. The crack section properties always have to be considered.
What will be the last time of yesterday's quiz? It is still open, so you can still go and submit the quiz for yesterday. For steel moment frame systems, the contribution of panel zone deformations to the overall story drift should be included.
Yes,
What does it mean?
it is required to be included. You cannot take a stiff beam column joint. That's what it means. The deformations that take place within the joint need to be modeled, need to be considered.
In Bangladesh, we do not have proper earthquake data. How can we use time history analysis?
I Bangladesh you may not have, but I don't know. I haven't looked into it, but if you do a literature search, you will find that in the foothills of the Himalayas and then going into Burma, this is a highly seismic area. So there are histories of all kinds of earthquakes that have happened. They haven't necessarily happened in Bangladesh, and that is unnecessary. The idea is earthquakes that can influence your structure. The earthquakes don't know geographic boundaries, obviously, they're political boundaries. So the earthquake epicenter can be in Burma and it can hit your structure in Dhaka. So what you need to look for is records of earthquake ground motion from, or you may not find records, but as much as you can find out about earthquakes that have had influence on structures in Bangladesh. And that is something I know that quite a bit of information is available. I have had no occasion to look into it seriously. Bangladesh Geological Survey may have information, I do not know. I'm sure there are sources of information. There are people who are, US Geological Survey is a good source to start with. They have information on seismicity around the world. So I do not have specific answer to your question, but the main thing I'm saying is that you don't look for record of earthquakes that happened in Bangladesh. The idea is earthquakes that affected structures in Bangladesh. So the epicenter could be located in India or Bhutan or Nepal or Burma or wherever. And if you look, I think you will find information.
Okay, Dr. Ghosh. So as per AC 705, the site-specific spectra is only required for site class F. Should we follow the same procedure? I am not understanding which procedure.
No, he is asking AC7 requires it for F, and is it do we do the same thing under BNBC or in Bangladesh?
Oh, okay.
Now, I I do not remember now. There is S sub 1 soil, S sub 2 soil. If you look at BNBC, the answer is right there. I don't exactly remember now where site specific is required, but it is pretty clearly indicated in the BNBC. What is type F soil is S sub 1 and S sub 2 in BNBC. For that, you definitely need it. But AC7 would require site specific for site E soil some of the time, site class E some of the time. And I believe it is similar in BNBC also, although I don't remember the details. It is not just for site class F. That is not true. I don't believe so. Let me check that one second.
Okay, Dr.
I don't want to give wrong answer. No, he's right. So AC705 did not require site specific except for site class F. That changed later. And this is my problem. I I can keep straight, what happened when. So BNBC will require site specific for site class S sub 1, S sub 2. Make sure that it does not require it for the type SE soil, which has later been required by AC7 for certain period ranges.
Dr. Um, so how to calculate number of required mode shapes, Dr. Ghosh covered in
Yeah,
his
that's the
presentation.
participating mass of
Uh,
90% at least.
what is mass participation impact factor also covered
Mhm.
during his presentation. Um, which method is better, Newmark beta method or Hodges method? Hodges method.
Say that again. Which method is what?
Which method is better, Newmark beta method or the Hodges method?
Or what?
You discussed it.
No, I do not know the answer.
Just check quickly.
No, he knows more than I do, so I don't have an answer.
Okay. Which vector is more accurate, eigen or Ritz? I think this is for eigenvectors.
I always thought that the eigenvalue analysis is more accurate than this Rayleigh rates, which is still kind of approximate. I'm pretty sure of that.
Okay.
Well, the eigen both depend on stiffness assumptions, so it is very difficult to give a blanket result, blanket answer. But yeah, generally speaking, yes, eigenvalue would be more accurate than something like Rayleigh rates.
Okay. So one person is saying that we also do not have any feel for metric numbers. It will be better for us if you keep both metric and FPS in the presentation.
I thought of that it becomes cumbersome. Yeah, I don't know. We'll see. Maybe we'll add those to the slide set.
What is the relation between mode and mass participation ratio? That is also covered. I think in the example it is very clear.
Hmm.
So in software calculated modal period is negative. Calculated modal period is negative. Is it acceptable? How is that possible?
I have no idea what a negative period is.
Yeah.
No idea.
This question came before. What should be the section modifier, stiffness modifier coefficient for beam slab?
For
It
what?
is 0 for beam slab.
Beam slab?
Yeah. He's saying that slabs and with beams basically. He's saying that we find coefficient 0.25 Iz for flat slab. Should
Yeah.
we use that's the same for the slabs with beam also?
I I'm not following the question because it all yeah, I don't know. I don't know what he means by slab beam and
No, he's saying that slabs which is supported on beams.
yeah, if it is supported on beams, that we would take the beam stiffness in our
Separately.
structural analysis, and part of the slab will be the flange of the beam. And if the flange is in tension, it has no impact. If the flange is in compression, that will add to the stiffness. So I do not know what he has in mind. That
No,
I
you answered.
Yeah.
That is what he had.
Okay.
Um, okay. Um, should we consider the stiffness modifiers for period determination also? Time period, basically.
Yeah, yeah. Yeah.
Okay, okay. And
The same cross section properties and so forth. Yes. No.
yeah.
Otherwise it's an artificial period.
In your previous lectures, you described that if structures they have torsional irregularities, we should use dynamic analysis. If we not,
AC7 requires that.
yeah, but the question he's asking, like, I'm not understanding. Yeah, so let me rephrase it. So in your previous lectures, you described that if structure have torsional irregularities, we should use dynamic analysis. That is right. If not, if we not want to reduce the irregularities, is it okay? If we so is it okay if we doesn't do dynamic analysis? I don't know.
No,
I'm not getting that.
AC7 requires it. If you are going by BNBC, it may be permitted. AC talks, I mean, BNBC talks only about vertical irregularities. Torsional is obviously not vertical. So if you are within the permitted height range, if you have torsional irregularity, BNBC, according to my reading, will permit you to not do dynamic analysis, but AC7 very specifically requires it. You remember it's one of the bad irregularities. So even for low-rise buildings, you need to do dynamic analysis.
Okay.
So there is difference between BNBC and AC7 in as to when dynamic analysis is required. No question about that.
So this question is not clear. Is it required to check the serviceability limits for dynamic analysis again when we are satisfied our structure in the ELF method?
I do not know. We talked about drip check, and I don't know. We satisfied. If you are doing dynamic analysis, we typically do static analysis only to figure out the static base shear. I do not, then the drip check is for the dynamic analysis. What other serviceability will check? I don't know.
At the drift only.
Yeah, so drip check we talked about.
You have to check the allowable drifts basically. So
Yeah.
yeah, I think that's pretty much it for today, Dr. Ghosh. Like,
Okay.
I don't see any other.
Okay. So thank you.